All right, in the first lecture on section 4.1, we looked at this idea of the change in f due to a small change in x, which we call delta x. And we said that this change in f could be approximated by taking the derivative at point A and then multiplying by whatever that small change in x is. What I'd like to do in this lecture is to do just a couple of examples of the types of problems that you'll be asked to complete for homework and looking at this idea of linear approximation. So, as I said in the first lecture, the idea here is that we're taking information about the derivative to make approximations to values of the function. In the examples we're going to do here that we do actually know what the function is, so the idea here is for us to be able to kind of look at this more theoretically in terms of seeing how that we can use the derivative here to make this approximation, to see how, if we know something about the instantaneous rate of change at a point and know how far away from that point we are, we can estimate how much the function will change. All right. So, for example, we were asked to, so this is we'll just call it number 1, we want to estimate delta f, all right, and we are given that the function is x minus 2x squared. They tell us that a equals 5 and that delta x equals negative 0.4. All right, so we'd like to compute delta f and then see how it compares with the linear approximation. And then I'll just make a quick sketch of that so we can see graphically what this all means. So first, we know that so delta f is just going to be f of a plus delta x minus f of a. So it's just going to be the change in the y value. How much does y change from a to a plus delta x? All right, and we know what delta x and what a are here, so we're looking at f of 5, so plus a negative, I'm going to say minus 0.4 minus f of 5. Okay, so this is f of 4.6 minus f of 5, and you can crunch the numbers, but you can just take my word for it in terms of the lecture. That is 7.28. All right. So when we go, well, I guess we can go ahead and draw a quick sketch here. We'll fill it in more later, but for right now, what we have is something that looks like this. This is a downward-facing parabola, something like this. We can basically call this 5. Here we are at 4.6. So right at this point, you can verify that that's going to be negative 45. All right. So we're going to have this other point right here. So this is kind of blown up, so it's not really drawn to scale. We could calculate this. It's going to be, well, this right here is our delta f, and that is 7.28. All right, so let's look at what the tangent line approximation would be. So again, we're using this formula up here. We've already calculated delta f exactly. Now we want to do the, so this will be f prime of a, so f prime of 5 times negative 0.4. We want to approximate delta f. All right, well, f prime of x is just going to be 1 minus 4x, so f prime of 5 is going to be 1 minus 4 times 5, or negative 19. So what we have here is negative 19 times negative 0.4, and if you do that, you will see that we get 7.6. So there's how they compare. Okay, so if we were to draw a tangent line at 5, so we could, kind of sketch something in like this. All right, so what we found was the tangent. So if we take this and kind of extend backwards, we're up here. So if we kind of look at coming over here, this distance here, that is our f prime of 5 times delta x, which we said was negative 0.4. So in this case, actually, the tangent line approximation of delta f is bigger, because in this case our curve is below the tangent line. If you recall, in the last example, actually I have it here just to refer to, since our tangent line was above, then our approximation was smaller than the actual delta f. In this example, because we have a downward facing parabola that's curving downward, our tangent line approximation for delta f, we said this was 7.6, is actually larger. So this piece right in here, that would be our error, which is delta f minus f prime of a delta x. All right, and we can actually compute that, right? It's just going to be the difference between, so it's delta f minus f prime of a delta x. It's just the difference between the actual change in f and the approximated change in f. So in this case, 7.28 minus 7.6, which we get to be negative 0.32. All right, so that's one example. I just want to do one more example. In this one, call it number 2, we're asked to use, to approximate delta f. So delta f being f of 3.02 minus f of 3. We are told that f of x is x to the 4th. So here we have to kind of read in here, right? So we can look at this and say, well, that means that a must be 3, and delta x must be equal to 0.02, right? Because this represents f of, this is f of a plus delta x minus f of a. So we can kind of work backwards from the numbers that they give us to deduce that a is 3 and delta x is 0.02. All right, so if we actually do this computation, we would get that f of 3.02 is 83.18. f of 3, which is 3 to the 4th power, that's 81. So delta f, and this is exact, the exact change in this function, if we increase the x value from 3 to 3.02, is going to be 2.18. So, but we also know that we can approximate delta f by f prime of 3 times delta x, which is, in this case is 0.02. So first we need f prime of x, right? So we have f prime of x. If f is x to the 4th, then f prime is just 4x cubed. F prime of 3 is going to be 4 times 3 cubed, which is 108. So we can approximate delta f with 108 times 0.02, which is 2.16. So very good approximation in this case. Let's just draw a quick sketch to kind of see what all this means graphically. X to the 4th looks a lot like x squared, except it just increases a lot faster. So we would have something that comes down, comes back up, should be symmetric, so just pretend if it doesn't look symmetric to you. All right, so let's say we're out here, let's call this 3, and we'll, again, not drawn to scale here, but we'll call that 3.02. So we going to put in our tangent line, or approximate it. Just kind of sketch something in here. Okay. Now, the tangent line approximation, right? So if we come this piece right here, that's my delta x. It's how much I've increased, x by. And then right here, this is the tangent line approximation, right? So that is f prime of 3 times delta x, which we said was 0.02. So that's that part, but we'd have to come up here on the function, right? So this right here is f of 3.02. Down here, again, not drawing a scale here, but just so we can see this is f of 3. So this piece right here, that's my delta f. It's the change in the function due to this small change in the x value. And then again, the difference, this is delta f minus f prime of 3 times delta x. And again, we can compute that, right? Delta f is 2.18. The linear approximation is 2.16, so that is going to be 0.02. All right, so that's just a few examples of how to apply this idea of linear approximations.